بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome back. In this second tutorial, we'll be looking at deriving the dynamic equations of motion. So we'll be using the Recursive Newton Euler Approach, the RNEA, to derive symbolically the mass matrix, the Coriolis-Centripetal matrices, and the gravity torques of a two-link planar manipulator. Okay, so we'll take this two-link planar manipulator that you see here in the figure, and this is simply a benchmark problem that we'll be deriving for the mass and Coriolis-Centripetal matrices as well as the gravity torques. Okay, we'll be computing them symbolically, and then we're going to be looking at trying to compare whether what we got is actually correct or not by looking at some references in the literature. What we're going to be doing here, okay, so we're going to be also using the modern robotics package and our helper function that we defined. So let's start by running them as well. We're also going to be defining symbolic variables L1 and L2 for the length of the both links, and Q1 and Q2 for the joint angles of the two links, of the joint angles of the two joints that we have here. The forward kinematics, we're going to be, to derive the dynamic equation, we need to solve the forward kinematics first, as well as the differential kinematics. So if you haven't watched tutorial number 1, you should do it now. So the forward kinematics will be exactly the same. There is a catch here, and it's very important to note that when we solve the forward kinematics and the differential kinematics, we only introduced a frame at the end effector and the base frame. Okay, so if you go back to tutorial number 1, you'll find that we only introduced the 0 frame and the E frame here. However, in order to do the dynamic equations, we also need to have a frame assigned to every link. And here there's a choice. Okay, we can define it anywhere on the link. In this tutorial, we're going to be doing it at the center of mass. Okay, so we're going to be placing joint 1 at the center of mass. So we're going to be placing frame 1 at the center of mass of link 1, and we're going to be placing frame 2 at the center of mass of link 2, as you see here in the figure. So what we're going to be doing now is that we're going to be computing the forward kinematics, but not only for the end effector frame, but also for frame 1 and 2. Okay? So, and we're also, in this two-link manipulator, we're going to be changing things a little bit. We're going to be taking this vertical position of the robot to be actually the home configuration, just to see how things change a little bit. So if you look at here, we have the two links. We have the two joints here. These are the screw axes of the two joints. And these are this is the base frame and frame number 1, frame number 2, and the E frame. So now, since we have these frames defined, we're going to be defining the home configuration of these 3 frames: HE with respect to 0, H1 with respect to 0, and H2 with respect to 0. So first, we'll define the rotation of E with respect to 0 and the displacement of E with respect to 0, given by this equation here. You'll see that what we have here actually is that, unlike what we had in tutorial number 1, where the rotation, the relative orientation between frame E and frame 0 was given by the identity matrix because they had the same orientation in the base frame. In the home configuration, what we see here is that so what you can look at here from the figure, so this rotation matrix actually you can easily deduce it from the figures here. So if you look at the orientation of frame E, we'll find that the X direction, which is the red arrow here of the E frame, is in the negative Y direction. So it's in the opposite to the green of the base. So we find that here this is the reason why we have the -1 here in the second row. So the first column corresponds to the X of the E frame. So and it's in the direction of -Y of the base frame. Okay, so this is why we have here. And if we look at the green axis here, which is the Y axis of the end effector frame, we'll find that it is in the X axis of the base frame. So the green here of the E frame aligns with the red of the 0 frame, which means that the second column will have 1, 0, 0, which is the second column is the Y axis, of the E frame, and it corresponds to the first, okay, so 1, 0, 0 in the base frame, okay, which is in the x-axis direction. And if you look at the z direction, okay, it actually doesn't change because this is simply a planar manipulator. Thus, we have the third column here to be 0, 0, and 1. Okay, so this is what we have here for the end effector frame. And the displacement here, we'll find that we have 0 in the x, 0 in the z, and minus L1 plus L2 in the y direction. And simply, this is what we have here. It's minus L1 plus L2 in the y direction of the 0 frame. Okay, so this is what we have here in the first one. If we look at the first frame actually has the same orientation as the end effector frame. You can see here the first, the second, and the first frame and the second frame of the two links, they have the same orientation as the E frame, and thus these two lines. As for the displacement, you see that actually that this we chose, and this is a choice that we did here. We're going to come back to that choice later. So we chose here to place the frame 1 at the center of mass, which is assumed here to be exactly in the geometric center of the link, and thus we have minus L1 divided by 2 in the y direction. Okay, so this is the displacement. So if we start at the 0 frame, you move minus L1 over 2. Again, then you reach the displacement. You reach the origin of the first frame. And if we go L1 plus L2 over 2 in the minus y direction, we reach, okay, here the second frame. Okay, and thus we have these three, okay, displacements. Now here, if we run them, you find this is, okay, what we just, okay, defined. As for the screw axis here, if you look at the first screw axis as seen in the 0 frame, we'll find that actually it's in the z direction, and it passes through the origin, and thus we have 0, 0, and 1, and 0, 0, 0, similar to what we had earlier. And if we look at the second axis here, as seen in the 0 frame, actually it's simply also the direction of the z-axis, while it is L1 displaced from L1, okay, in the y direction. So we would choose here this point here because it's the easiest one to actually compute with the screw axis, and so we have minus L1 in the y direction. Okay, so this is how we define the screw axis. That's it. So this is all of the piece of information that we need. So we are exactly there. So the only thing that is now in addition to what we did earlier was simply H10 and H20. So if we have n links, we need to define the home poles of all of these frames that we attach to each link of the road. The product of exponential formulas, we're going to be running it again and again. So we're actually going to be running it here for the end effector poles, and we're going to be running it here for the frame 1 poles and for the frame 2 poles. Okay, so you see actually the end effector is simply given by the product of exponential formulas. The product of exponential formula is actually applicable for any frame here. Here we multiply the exponential of the first screw axis multiplied by the exponential, multiplied by the exponential of the second screw axis multiplied by the home configuration of the end effector frame. We do the same here, okay, for the first frame, but we only multiplied by Q1 by the exponential of the first screw axis, and for 2 we multiplied by exponential of 1 and 2. But here we have used, instead of E with respect to 0 in the home configuration, we use 2 with respect to 0 in the home configuration. So we run this and find, okay, these are exactly the same. Okay, very, very similar to what we had earlier, and they may also make sense. Okay, you can check with, you can eyeball them, just take a look at this figure, and you can actually see that it indeed, okay, depending on Q1 and Q2 starting from this home configuration, this is the rotation matrix and the displacement of the end effector. The differential kinematics are exactly the same as what we did earlier. We will also be doing it for the first frame and the second frame. So this is very similar to what we did earlier for the first joint, sorry, for the end effector, sorry. And this is for the first one, and this is for the second one. So if you look at here, the first, the spatial Jacobian of the first link, you'll find that actually it's simply just, it has zeros. It's actually what we have here, recall that the geometric Jacobian in this case is a 6 by n, which is a 6 by 2 because we have a 2-link manipulator. And in the case of the end effector, both columns, they were filled. This was the first column, this was the second column. The second column of the Jacobian, the geometric Jacobian of the first link will actually be zeros, while the first column will be the same as what we had in the end effector. As for the second link's Jacobian, it's actually exactly the same as the end effector. Okay, it's very easy to check that that's the case, simply because if you look at here, that the relative transformation between the link 2 and the link E, the relative twist between them is actually 0, which means that actually they both have the same geometric Jacobian. So the Jacobian actually is geometrically defines the velocity of the link we're talking about. And since frame 2 and frame E, if you go back to this picture here, so frame 2 and frame E, they are both body fixed to the same link. And as this link moves, they change in the same with the same velocity, with the same twist. In the end, they actually correspond. They have the same Jacobian. Okay, so that's the intuition behind we have here that J2 with respect to 0 expressed in 0 is the same as E with respect to 0 expressed in 0. And to transform these Jacobians, the 3 to the frame 2E and frame 1 and frame 2. So we're looking at the body Jacobians now. We can simply use the joint transformation. And actually, if you look at now these 3 expressions that we compute here, you'll find that the end effector, the end effector Jacobian, which is expressed in the end effector frame, which is given by this expression, is actually different from the one of the second link. Okay, simply because now we have a transformation between both. So in the spatial frame, they are both the same. However, the twist of link number 2 expressed in the 2 frame, it will be different from expressed in the E frame. Okay? Even though they're both attached to the same body, they are actually different because you get different numbers if you express in different frames. Okay? And thus, what we have here is that these are actually, they look different. Okay. So simply, we don't need these expressions, and this actually, we're going to be computing, we're going to be using them later on. Okay, so that's it for the kinematics. So what we did so far is that we computed the forward kinematics and the differential kinematics of this 2-link manipulator. Now we're going to be starting to implement the recursive Newton Euler approach, but before that, we need to also introduce the inertia parameters of the 2 links. So we have 2 links, and thus we have 2 generalized inertia matrices. In this tutorial, we chose to have the frame 1 and frame 2 placed at the center of masses, which means that the generalized inertia will be given by an expression that looks like this. So actually, I'll just run it. So this is actually the expression of the 2 inertias. We have the mass of link 1 and mass of link 2, okay, in the bottom right corner, multiplied by the identity matrix. In the top left corner, we have the moment of inertia matrix of link 2 and moment of inertia matrix of link 1. And in the off diagonal parts, they are all zeros. Okay. What we did here is that we symbolically defined M1 and JXX, JXY, XZ, and so on. So all of the 6 components. Recall that the moment of inertia matrix is a 3x3 matrix. It's symmetric, which means that it doesn't have 9 independent parameters, but rather it has only 6. Okay. So the 6 variables, so if you see, because it's symmetric, we have X, Y, Y, and Z, Z. Then we have X, Y, X, Y, X, Z, X, Z, and then Y, Z, Y, Z. So it's actually a symmetric matrix. It's a symmetric 3x3 matrix, and thus we have 6 independent parameters. We're going to be deriving it symbolically here, and later on we're going to be plugging, in a future tutorial, we're going to be plugging numbers, and we'll show you how to do that later on. So that's it. So this is all of the piece of information that we need to provide. So we need to, just to recall, we need to provide the home configurations of all of the links that we have, of all of the frames that we have. We need to provide the screw axis in the 0 frame. We need to solve the differential, the forward kinematics problem using the product exponentials formula. And then we also need to compute the spatial and body Jacobians by solving the differential kinematics. And we also need to provide the inertial parameters in the frame that we chose. So here we have in the frame for frame 1 and for frame 2, this is how the inertia matrices, the generalized inertia matrices look. And now we're able to run the recursive Newton Euler approach. The recursive Newton Euler approach is very systematic. Okay, in order to, before we start that, we're going to be transforming, okay, the screw axis that we defined in the 0 frame to frame 1 and frame 2. Okay? And to do that, we can use the adjoint map, okay, simply by these expressions. And we're also going to be needing the relative transformation, the relative pose between every link and every parent link and its child. So the parent with respect to child. You see here we have 0 with respect to 1, and we have 1 with respect to 2. Okay, so the parent, which is 0 here with respect to the child, and the parent with respect to the child. Okay, and this simply we can redo this computation for any links that we have here. Okay, so this is simply just a few transformation matrices that we're going to be computing from what we already did before. So that's it. So these are just intermediate computations because we're going to be needing them. And now we can start to build up all of the block matrices that will make up, that we're going to be using for the recursive Newton Euler approach. This is the S matrix, which is block diagonal of the screw axis, each one expressed in the child frame. And then we have the block diagonal form of the generalized inertias. We have the matrix A of Q and L of Q. And this is simply the J of Q, which is L of Q multiplied by S of Q. These are all defined in the lecture. You need to go back here at this point to the lecture to actually review. This is how these matrices look like for the case of the two-link manipulator. There was at one point, if we go back to the lectures, we're going to find actually that this J matrix we're actually defining is the same as the body Jacobians, okay, just stacked over each other. And here we can actually check this claim. So it was actually shown theoretically. Let's actually compute this symbolically here. What you see here, this is how J of Q looks like. Okay, this is J of Q that we compute by just multiplying L of Q multiplied by the S matrix. Okay, so it looks like this. You see actually on the first part we have what looks like J1 with respect to 0 expressed in 1, and J in the second part, so the second 6 by 2 matrix is actually J2 with respect to 0 expressed in 2. And actually, if you look at here, you find actually that's exactly the same, what we have. Okay, so we actually are just comparing, this is just a sanity check to see actually that the theory that we have is consistent and all of the computations we're doing are consistent. Okay, so we're not going to be needing this later on, so this was just a small test to check for that. In order to compute the Coriolis-Centripetal terms, we need extra. So these are what we need so far. We can actually, at this point, we can compute the mass matrix. Okay, what we're going to be doing it later. So you see here, this is how we compute the mass matrix. But there are a few extra terms that are needed for the Coriolis-Centripetal terms. Okay, and these are, I'll leave that for you to look at your own pace. And so these are extra terms that we need to derive the Coriolis-Centripetal terms. One of them actually is the A dot. So if there was in the lecture an expression that we had the A matrix, so this A of Q, and there was an A dot of Q. We're not going to actually compute the A dot by numerical differentiation. There's actually a closed form expression for it, and it simply it's given by this expression here. This was not derived in the lecture, okay, but it's easy actually to check. If you're interested, you can just look at the lecture notes. You're going to find this derived in the lecture notes. So now we computed all of the pieces that we need to compute the dynamic of the reduced dynamics of the manipulator, and this is how the mass matrix will be computed. So actually we can compute it simply by multiplying the I matrix, which is this one. You see actually if you just hover here, find this actually how the I matrix looks like. It's just simply the two generalized inertias of the two links, but stacked in a block diagonal form. And then we have the J here, which is a 6 multiple. It's a 12 by 2 matrix, so it's a 6n in general by 6n by n matrix. And if we multiply these two in the end, we're going to find that actually this is the J transpose. So J transpose multiplied by I multiplied by J. In the end is the definition of the mass matrix, and we're going to be simplifying it, a little bit. And this is how it looks like. Okay, the centripetal terms, they are given by this expression. We also simplify them. This is actually a very important part. I'll come back to that later. But if you remember that, if you go back to the dynamic equation, the Coriolis-Centripetal matrix actually never appears alone. It's always multiplied by Q dot. So if we multiply the C by the Q dot, okay, we're going to be calling it, we're going to be doing it in this line, this one. So this is actually the small c here symbolically is simply C, the capital C matrix multiplied by Q dot. Okay, where Q dot here, if you go back, is actually the vector of Q1 dot and Q2 dot that we have. Okay, the gravity torques. Okay, so this is also, you find it in the lecture. So this is actually also how we have the gravity defined, and is simply given by this expression here. Okay. So now what we did so far is that we have the M matrix, we have the C multiplied by Q dot, and we have the gravity torques. Okay. So that's it. So this is actually the derivation of the manipulator equations for the two revolute planar manipulator that was shown in the figure above. And actually, the reason actually why we chose this two-link manipulator is actually because it's a benchmark problem, but it's also available in the book of Lee, Murray, and Sastry. So this is actually a very classical book. It's actually a predecessor of the modern robotics book by Kevin Lynch and Frank Park. And this is actually a very nice book if you're interested to take a look at it. And you'll find here in chapter 4, section 2.3, that actually the dynamic equations of the two-link manipulator that we looked at above, excluding the gravity, are given in this expression. And they're actually, you can take your own time to actually double check whether actually that this mass matrix, which is exactly the same as this one. Okay, so I already did the check. So, but I leave that as a homework for you to really do it at your own pace. So I'll end with a very important remark, and it's as follows: that if you take a look at this C matrix, okay, so this is the Coriolis matrix that was defined here in the book, and the C matrix that we computed, which was actually this one, we did not print it yet, but this is the C matrix here. Compare these two C matrices together, okay, you can clearly see they're not the same. Actually, without even going through the details of actually, expanding these expressions, you find that actually that the second row, second column element is actually 0 in the C matrix that was provided in the book, and the C matrix that we have here is actually doesn't have 0 in the bottom right corner. And this is actually something very important, and it's stated as follows: that the C matrix itself is actually not unique. So there are many ways that we can define the C matrix. So the way we derived it here symbolically is led to this expression, while the way that was derived in the book here, I suspect it was by using Euler-Lagrange equations, is actually given by this expression, and they are not equal. And this is a known aspect of the dynamic equations of manipulators in general. That the C matrix is always not unique. The mass matrix is always unique. So, but the C matrix is not. However, when you multiply the C matrix by the Q dot vector, okay, so the joint velocities, you always recover the correct expression. Okay, so that's why this is the reason why we multiplied C by Q dot here. So if you compare this expression which is the C multiplied by Q dot to the C matrix multiplied by Q dot of this expression, you'll find they have to be exactly the same. Okay, so just to conclude, so the C matrix is not unique. However, the product of C multiplied by Q dot is always unique. Okay, so that's it. That's the end of the second tutorial.